right now. I'll talk to my 6 hour today regarding this as well. Okay, if all my students do what I ask about bringing the 55 cans in, that's how many cans all my classes would turn in. Almost 8,000 cans. Okay, which is over half the goal for myself, Mr. Webster, and Mr. Chambers. So I think it's very possible for this thing to be done. Okay, absolutely. In fact, if all students were able to bring in just 10 cans, we have 2,000 students here. If every student just brought in 10 cans, 20,000 cans right there. That right there would be awesome. That would be awesome. Cool?
Yeah.
Got it? So I'm going to have that post there so we have our competition, things like that. So as of right now, you guys are ahead with the highest number of cans per student. Because you guys have the least amount of students in here.
Yay.
All right? It's counting, so it is proper sig figs.
It's
It's counting.
I did not say that.
No, you said it.
I give credit to him. He said it.
All right. So, this was your homework problem.
Yeah.
It was fun.
It was fun?
Yeah.
Pretty easy?
Yeah.
He was
So easy?
Yeah.
I wanted to die.
I thought I was. It was so easy. I was just falling asleep doing it.
So easy you were doubting yourselves possibly?
Yes.
Okay, so you guys probably did it one way.
Oh, we all. Which is the wrong
The easiest way.
Which possibly could be the easiest way. All right. However, this one right here, there's definitely more than one way to do this. More than one way to do this. And one way is a whole lot easier than the other. So we want to go through both of these ways to make sure you have things. Okay? All right? Okay. So, situation already, givens, unknowns. We've got free body diagrams. As we talked about yesterday, you've done the free body diagrams for both these things already. So that was pretty much just a matter of copying your work. So mass 1, we just have weight going down, weight 1 going down, tension going up. Equations are easy. Force in the x direction, 0 equals m1 ax, and it's not accelerating. Force in the y direction, tension minus weight 1 equals m1 ay, which equals 0 because mass 1 is not accelerating at all. Easy, right? Mass 2. Again, we did this free body diagram in class already and checked over. We know that weight 2 goes down. Tension is on an angle. We broke up into components. This right here is theta. So T cosine theta, T sine theta. No problems. Now is the new stuff. We didn't do the equations for this in class. It's where you guys' application comes into play here. So if we do force in the x direction, we have T cosine theta, but it's pointing to the left, making it negative. Equals M2A. Is it accelerating?
Yeah.
Yes, there's only one force and there it has to accelerate. Which way is it accelerating?
Towards the
Towards the center. In this case, which way is the center from this point of view?
To the left.
To the left, making it negative. And what kind of acceleration is it? Center seeking, which is called centripetal. So therefore it's NAC. How many people out there forgot the negative sign with this? Do you guys realize that now? Okay. Remember, ask that question. Which way is it accelerating? Force in the y direction. Okay. We have T sine theta minus weight 2 equals M2AY. Is it accelerating the y direction? Nope. Equals 0. And that's the physics. All right? What's our next step?
Manipulate. Oh, yeah.
Go through the unknowns and knowns. Exactly. And underline. Okay? This equation really doesn't count for anything. Okay, do we know tension? No. Do we know weight 1? Yes. That takes care of that. Over here, do we know tension? No. Do we know theta? No. That's what we're solving for. Okay? Do we know mass 2? Yes. Do we know AC? No. So this equation, we have 3 unknowns. Here, do we have tension? No. Do we have theta? No. Do we have weight 2? Yes. Equals 0. So if we look for this 1 unknown, 2, 3 unknowns, we have 3 unknowns. And we have 3 equations, which means we can solve for it. What are we trying to solve for? Theta. And theta is located either here or here. Between these 2 equations, which one would you choose?
The bottom one.
Bottom one?
Yeah.
Why the bottom one?
Because it equals 0.
It equals 0, but also has 2 unknowns, less things. But this one has 3 unknowns. In order to solve for theta, what do we need to find first? Tension. Where else can we find tension? This one right here. So we take this solve for tension, take it and plug in there, right?
Yeah.
Easy. We've done that before. The tension is equal to M1G. Plug into here, M1G sine theta equals M2G. Right?
Yeah.
We know mass, we know gravity, we don't know theta. We know mass, we know gravity. Solve for theta. How do we do it?
Divide by M1G.
Divide both sides by M1G. So therefore, sine theta equals M2G over M1G. Do the G's cancel?
Yeah.
G over G, they cancel. Good. And now solve for theta. Inverse sine of both sides. So therefore, theta equals inverse sine M2 over M1.
So wait, doesn't this mean that you could be like anywhere, like in the universe?
Does this mean this can happen anywhere in the universe? Absolutely. As long as I'm able to swing this thing around in a circle, for sure. So what this tells us is we don't need no, this tells us that we don't need no length of string or time. All we need to know is how much mass there is. That's it. How much mass is here and how much mass is hanging from it. And what that also means, it doesn't matter how long the string is as it's going around the circle. It can be this long or it can be this long. That angle that's created is the same. That's what this is showing. No matter how long the string is, by the way I'm twirling it, that angle will always be the exact same. Whether it's like this or like this, that angle will always be the same. We just need to know these 2 masses. Yes, sir?
So then, if like the equation doesn't have speed, then
Correct.
how come when you made it faster, then like why did that make it change?
Why did it make it change? Okay, so when I had this thing twirl around, depending on how fast it was going, is where there was an equilibrium, right? So when it was like here, long string, it looked like it was taking a long time to go around, correct? But if I had it shorter, it took less time to go around. So the length of the string and how much time it takes to go around, those do kind of compensate for each other. Does that help out? Good? That was probably the way that most of you guys probably did it, right?
Yeah.
The easy way. Okay? However, as I said, this right here is one answer. And the other answer we get will look completely different. It'll look like a completely different equation. And we're going to do that. And the reason why we're going to do that way is because, did we even use this equation right here? No. But this chapter is about using this, MAC. So therefore, I want to take a look from this point of view, using this equation. Okay? Does that make sense? Okay, so we want to find theta. We've already found tension according to you guys with this, correct?
Yeah.
So therefore, the only other way to find theta is we need to find AC. So that's what we're going to start. Okay, so very much like anytime we have friction force, we always write the fun equation. Right? Anytime we have centrifugal acceleration, AC, always write v squared over r. Because that's what centrifugal acceleration is equal to. Okay? AC is an unknown. Do we know the velocity, the speed? No, that's another unknown. Do we know the radius? Yes?
Oh, well, no.
Yeah, it's like we have the length of the string. Length of the string.
Is the length of the string the radius?
Yeah.
Divided by half?
No, why would you? It's already.
Okay, so some people are saying yes it is, and other people are going to go, no, it's definitely not.
Let me get the question.
Did we had this discussion yesterday, didn't we? I thought we did. Is it the radius?
No, it's not.
If this is the radius, that means it's going around an angle like this. But is it? It's going around a horizontal circle like this. And where's the center of the circle? The string. Therefore, from here to here is the radius. Not T. L is the length of the string. And here's the angle. Now this right here would be the radius. So we do very much similar to what we did with the vector diagrams and whatnot. This does become L cosine theta. I'm really curious to find out what movie they're watching next door.
Yeah. Always watching a movie. I'm just gonna join them.
No.
Oh, you watch
Can I send?
No, that's Webster. So, the radius was an unknown. And that radius is L cosine theta. However, it has the unknown we're looking for in it, which is 5. So we're not going to find an exact value for it. We're going to express R in terms of what we know. Good? Next thing we need to figure out is V. Velocity. How do we find velocity? Delta D over delta T? What does delta D refer to? Distance. Good. So what's our distance going to be? The circumference of the circle. So our distance is circumference divided by the time it takes to go around that circle. Do we know the circumference? No. But what does circumference equal to? 2 pi r. Good. 2 pi r. What is r? L cosine theta. 2 pi L cosine theta divided by time. So now we have expression for velocity in terms of what we're looking for. So therefore now AC is expressed in terms of what we're looking for. So now we're going to take this and plug it in. But first, let's actually substitute it into here first, just to simplify some things. AC, V squared, so this quantity right here, 2 pi L cosine theta over delta T. That right there is V, that's being squared, divided by L cosine theta. Yuck, I have a compound fraction. Multiply by what? Reciprocal. So instead of dividing by L cosine theta, we're going to multiply by 1 over L cosine theta. Got it? But in addition, I want to take this square and distribute to each term in here. Okay? So therefore, this becomes 2 squared, 4 pi squared, L squared, cosine squared over T squared times 1 over L cosine theta.
It becomes 4 pi squared L cosine theta all over delta t squared.
No, L squared. L squared.
No, you're dividing. The square.
No, you.
No. The denominator is L cosine theta.
No,
Oh, I was-
Would the denominator just be L cosine theta delta t squared?
Yeah.
Absolutely.
Yeah.
But something else happens.
Yeah, so it's not, doesn't it become just one cosine? They don't cancel, but it just be L cosine.
Yeah, L cosine theta.
L squared on top and L on bottom.
One of those L.
So this one goes away, but leaving one on top.
Yes.
Same thing true as the cosine?
Yes.
Okay. So it does simplify. So therefore AC becomes 4 pi squared L cosine theta over delta t squared. Are we good? Got it? So now I'm going to take this and plug it into AC up here. Good? So this now becomes T cosine theta equals M2 AC, which is 4 pi squared L cosine theta over delta t squared.
Is it negative? Yeah.
Oh, it would be negative t. Didn't I have a negative sign right here?
Yeah.
Okay, but doesn't this also have a negative sign?
Yeah.
So that they cancel each other out? Yes. Sorry about that. Okay? Got it? Okay, what are we trying to solve for? Theta. Where is theta? Here? And here. They're on opposite sides. It's not good? No, but we need to get them on the same side, right? How? Divide? If we divide both sides by cosine theta, does it go away here?
Yeah.
And therefore, does it go away here?
Yeah.
Yes, it does.
But then you don't have.
What's another way to get them all on the same side?
Subtract.
If I subtract this whole thing to the other side,
Yeah.
then this side equals 0. Is that okay? They have a cosine term minus another cosine term, factor up the cosine, right?
Yeah.
So cosine times something now equals 0.
Oh.
Is that going to be helpful?
No.
No. In fact, that's worse. Do the cosine thetas cancel?
Yeah.
Yes, they do. Now we don't have theta anymore, do we?
That's what we use the other.
But we still have t,
Yeah.
right? Does t have theta in it?
No. No.
Not according to that one. However, here. Could we take this equation and solve for t? Because that has theta in it. So that's what we're going to do. Bring the w to the other side. So t sine theta equals m2 g.
So you did all that work for basically.
It looks like everything goes away. So nothing's going to happen because we got rid of the thing we're looking for. That's not good. So somehow we need to bring it back. And that's where this equation will come into play here. Because could we take this and solve for t? So t equals m2g over sine theta. Could I now take this and plug in for t here? Yes, and now theta is back.
This just makes it more complicated.
It's a mess? It's not really a mess.
I think it is.
It's a whole lot more complicated than the other way, right?
Yeah.
Okay, if you want to call that a mess, then fine, it's a mess.
I was thinking organized.
An organized mess, organized chaos. Maybe from your point of view. Okay?
One over M2.
1 over M2.
You want two G.
Multiply both sides.
By M2G.
If we multiply both sides by M2G, what that leaves is 1 over sine theta on this side. Theta is what we want to look at. It's a denominator. We don't want a denominator. Could we cross multiply? Fraction equals a fraction.
Sure.
And does that get rid of the fractions part of it?
Yeah.
So therefore no denominators, right? So let's go ahead and do that. So if we do that, we get M2G delta T equals delta T squared, thank you. M2 times 4 pi squared L sine theta. Divide by what? This right here? Okay, so when we divide both sides by that, we get M2G delta T squared over M2 4 pi squared L equals sine theta.
Take the inverse
Hot part?
Take the inverse
Take the inverse of both sides? Before we do that, what can happen? Can the M's 2 cancel each other out? Absolutely. Okay, and now we'll take the inverse of both sides. So therefore, theta equals this inverse sine of G delta T squared over 4 pi squared L. And this looks completely different than the other equation, doesn't it? What thing is not here? What things are not here? M1 and M2. So what that means with this equation, I can grab any two masses that aren't even marked and attach it to this string and start twirling it around. And you're going to measure how much time it takes to go around and the length of the string. And that's all the information you need to figure out that angle. It doesn't matter what masses. Pardon? Does it only work on Earth? If this G just represents the acceleration due to gravity on Earth, but could this G represent the acceleration due to gravity on any planet you're on?
Yeah.
Yes. Does that help out?
Yeah.
Okay. So this can be done on a surface. Good? That's what this right here shows. It doesn't matter what mass I have, as long as we can time how long it takes to go around and the length of that string, we can figure out what that angle is. So furthermore, what this shows is the following. G, is that a constant?
Yeah.
Let me make it look more like a G as opposed to 9. It might be worse, but whatever. Okay? G is a constant, 4 pi is a constant. This thing is just dependent on how long it takes to go around, squared, and the length of the string. Right? And then that's inverse side of that is theta, right? Which means M2 over M1 is equal to this. Pardon? So this and this is the same thing, which means this ratio of masses is proportional to this ratio right here. What's that? Okay. That's what this represents. The reason why I'm doing this is because if I give you a question or I gave you an experiment to do to try to figure out an angle, and I give you a list of information, or sorry, a list of things that you can use to discover this angle. If I just say you have a bunch of masses and that's it, can you figure out what that angle is?
Yeah.
And just by taking a look at this right here, would you know for a fact it's going around in a circle or not? Just by taking a look at this, do Do you know if it's going around a circle or not? No, you don't. If we take a look at this, can we see if it's going around a circle? Why? 4 pi squared, right? 4 pi squared, same thing as 2 pi quantity squared. 2 pi, that's a circle. So this, we can clearly see something's going around in a circle. This, can we see if something's going around in a circle? No, we don't. And that's why this way is a better way for what we're doing now. It's more complicated steps-wise, but it fits for what we're currently doing. Okay? One of the things I told you after the last multiple choice thing I gave you for online was introducing more lab stuff. If I said you have the following piece of equipment to figure out the angle at which this thing is at, what piece of equipment would you actually use and what would you do measure? Okay? Masses, what piece of equipment would you need to use? Just a scale. What happens if a scale was not available? Could you do it this way? No. Because you don't have a scale available. How you found out the mass? Okay? However, what tools would you need to use in order to find it this way? Ruler and stopwatch? What would the ruler measure? Length. What would stopwatch measure? Time. Got it?
It's like 2 tools though. That's good.
Pardon?
It's 2 tools instead of 1.
Exactly. 2 different tools. As opposed to just 1 tool. You got it. Good? Questions? So as I said, the reason why I want to show you guys both ways is for that fact that if you have a lab type question, you'd know how to take a look at from. Good? Cool? Questions? All set? Excellent. Okay. One last thing then. It has to do with the discussion that this class had just a little bit yesterday, just a little bit. Okay? And this is the only class that had the discussion of going around in a circle. Going around in a circle. Not necessarily walk around the circle. Going around in a circle. A particular circle that actually deals with this school. Circle drive. And how would you go around the circle? Would you walk around the circle? Or would you drive around the circle? I want to know how fast can you drive. Do not try this. Do not try this. And no, this is not reverse psychology happening here. Do not try this. Don't do it. Don't. Please. How fast can you go around the circle drive? Now, yesterday we had a discussion about what allows us to go around in a circle. Friction. And which way does friction act in us as we're driving around the circle? Inwards, because which way does a car feel like it wants to move? Outwards. If you go too fast, what's the car start to do? Slides outwards. And we want to know how fast can you go around the circle before you start sliding. So what kind of friction are we talking about? Static friction. You got it. And we're going to assume it's a dry day. Dry. Because once you add water, bad things can happen. Yes, it's a very dry day today. And again, do not do this. Blind corners. We talked about that yesterday too, didn't we? Lots of blind corners. Huh?
Wait till like later.
Don't do it. Don't do it. Okay? Maybe you can say it loud enough that they can hear me next door.
What are the odds?
You no, don't.
And I'm gonna say,
Please.
Yes,
N-O. Okay. All right. So, let's take a look at this. Friction. Coefficient of friction. What's it going to be? Static. Yes, that's a symbol mu. Okay. What things are in contact with each other? Tires, which is made from what? Rubber. And concrete, dry concrete. The coefficient of static friction, that is 1.0. Okay? What other information do we need to know about the circle drive? No, not really. You should just kind of go like this. The circumference? Okay. So we're not going to measure the circumference. Can we measure the radius? If you go on to Google Maps, you can actually measure the radius of it. But you need to know where the center of the circle is. Okay, draw a couple different diameters for a circle. Where two diameters cross, what does that mean? Where do they meet? Center. Where is the center of the school? Commons? Okay, and there's a particular thing in the, did we talk about this yesterday?
No.
No, we didn't? Okay, there's a particular thing in the commons that's almost the very center. The peak of the skylight. Okay, the skylight itself is a square pyramid. And where it meets the very top, if you actually take a look at Google Maps, it's almost the center of the circle drive. It's off by like a couple meters. It's pretty darn close. But we can measure using Google Maps what the radius is, and therefore we have the circumference and things like that. So we can measure the radius and we have the coefficient of friction. Those are two things we have. What other pieces of information do you think we possibly need to do this? Mass of the car. And mass of the car, no problem. You can look up your own mass of the car. It's pretty standard as far as I go. It's probably possibly even stamped on a sticker on your vehicle too. Good? Got it? Okay, so those are the things that we can measure or have. Okay. Draw the situation. We're not going to draw the situation. We kind of save some time here. Okay? We're going to start. We don't know what the givens are: radius, coefficient of friction, and the mass. We're trying to figure out how fast you can go around it. So what we're looking for? Velocity. You got it. We're looking for velocity or speed. Okay? So now free body diagram. From which point of view are we going to draw our free body diagram? Side? Top? Okay, if we take a look from the top point of view. If we take a look from the top point of view, what will we not be able to see? Weight and normal force. We would not be able to see those two. Is this thing dealing with friction? Do we need to see normal force? Yes, so therefore top point of view is out. Side point of view. If we take a look from the side point of view, that means I'm staying within here and looking if the car goes around, right? Is it going around a circle? Which way is the center of the circle? Behind me. Is that from a good point of view then? No, so therefore side point of view is out. Would front or would back work? Yes, either one of those two would work. So therefore we're going to take a look at this from a front or back point of view. And here's my car.
Mr. Mouse, like, we have to say what point.
What point of view? You got it. When we're going around the circle, we have to say which point of view. Absolutely. Yes, ma'am. Quick. Okay. With that big, huge keg of drink, yes, I'm sure. Unless that's not you. Okay. All right. And her ID. Okay. What force are acting on it, folks? Weight, friction, and normal. Which way does weight go? Down. Good. Normal force. Up. Friction force. Inward toward the center circle. Okay, let's say the center circle is over here. So which way is it going? To the right? Okay. Yes, sir. Correct. So that's where the drawing the situation would come into play. So based upon where your car is in the drawing, that's where it go from. Does that help out? Okay, very good. Anything else in contact or field forces? No? Free body diagram is done? Angles? No, we're all good? Fantastic. So this is easy, right? Force in the x direction. We just have friction force. Equals MA. Is it accelerating? Yes. Which way is it accelerating? To the right. So therefore it's positive. What kind of acceleration? Centripetal. Center seeking. Centripetal. Done. Force in the y direction. Normal mass weight. MAY. Is it accelerating the y direction? No. Good. Those are the equations. Go for the free body diagram. Because we have friction force, automatically write down fun. It's static friction. Because we have centripetal acceleration, automatically write down AC, V squared over R. Okay? Physics is done. Time for math. Going through the equations. Do we have friction force? No. Do we have mass? Yes. Do we have AC? No. Do we have normal? No. Do we have friction force? No. Do we have mu? Yes. Do we have normal? No. Do we have AC? No. Do we have V? No. Do we have R? Yes. Good. Now, what are we trying to look for on the overall? V. We're trying to look for V. When we're to find V, we need to find AC. When we're to find AC, we need to find friction force. When we're to find friction force, we need to find normal. We find normal. And now it's just a domino effect. So solve for normal. Normal equals mg. Plug in for friction force. Friction force equals mu s mg. Plug it in up here. US mg equals m AC, where AC is V squared over R. All the substitutions are done. Do we know mu? M, G, M, V? Is that what we're solving for? R? Yes? So we have everything here except for what we're looking for? Solve for it. Solve for V. You guys done yet?
Yes.
What happened to mass? It's canceled. So according to this, supposedly, according to this, does the mass of the car matter? No. Therefore, supposedly, it doesn't matter what kind of car you have. However, do some cars tip over easier than other cars?
Yes.
That's what this thing does not take into consideration. That's one of the things, one of many things why I say, don't do this. So what do we really need to find? What do we really need to measure? The radius. Once we have the radius, we're done. And we can figure out that velocity. Got it? Now, just to let you know, folks, by plugging things in, you can get right around 75 miles per hour. Think about trying to go around the circle drive at 30 miles per hour. That's kind of fast. 40 miles per hour. That's still fast. Seeing you guys whip out of here today after school because you want to get the hell out of here because it's vacation time. Might see 50 miles per hour. Don't do it. Do not, folks. Do not test. Hang on. Stop for a moment. Don't test this. Now, we're making many big assumptions here. One assumption is that this circle drive is nice and flat. It's not. It's actually tilted. Okay, so bank curves, we tilted. We're going to start with that on Monday when we get back from vacation. Okay? All right, and that is correct. No homework. It's vacation. Why would I give you homework or vacation?